Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to provide an example of how to apply Newton's second law for rotation. So let me chat a little about what we're looking at here. So imagine we've got this large disc-shaped geometry here, this 10-kilogram object that has a 50-centimeter radius that's free to rotate about some sort of axis. And it's being driven by a pair of belts, some sort of belt that comes around here. Which is being driven by this wheel in some way, shape, or form. So imagine this wheel now is being turned in this direction in such a way that we have a tension in this belt of 50 newtons and a tension in this belt of 30 newtons. What we're going to do is we're going to try to calculate the delta t here, the time it takes for this disc to go around 100 times, 100 revolutions. Now, first let's talk kind of basic method, like how might we do that? Well, the work energy theorem is something we could apply to this, but the work energy theorem doesn't have time in it anywhere. Now, what we could get out of it is maybe some sort of final angular velocity, and from an angular velocity graph, we may be able to get that time. But what I'm going to do here is I'm going to choose to use Newton's second law for rotation. And in order to do that, we need to draw a free body diagram of this object. So I'm going to clone it here. And for the purposes of drawing my free body, now I talk about these tensions. So the tension in this part of the belt here is 50 newtons. So I'm going to go ahead and put a force vector on there for that 50 newtons. And that's going to be in this direction. I'm going to call that T1, or I guess I've already called that T1, 50 newtons. Right. In addition, we have a 30 newton tension in this belt. And again, if our free body is of this object, that 30 newton tension is going to be maybe something like this. Now, it doesn't say whether or not this problem is horizontal or vertical or whatnot, so I'm going to hold off on that gravitational force. But no doubt this pin is going to have to put some sort of horizontal support on this object so that it doesn't start accelerating to the right. So there's going to be force at the pin. I'm going to call that, how about F, actually I'll go back and call it PX. PX, force at the pin X direction, and force at the pin Y direction. And again, the direction here wouldn't be 100% clear, but that's why we'll just put it in component form. Now, whether gravity is a factor in this problem, I mean, whether it should go in the free body or not, I haven't talked about the orientation of this. Perhaps this is like a top view where this thing is rotationally this way, where gravity would point right into the page. Or perhaps this thing is horizontal, where the gravitational force would go straight down. It turns out it's not going to matter. Let's say, for the sake of example, that this thing is horizontal. So in this case, the gravitational force applied right here would be pointing dead away from you, almost in the direction you're looking. There would also be a normal force of some sort, or force at the pin, coming right at you. Well, this thing's not accelerating into or out of the page, so those forces would add to zero anyway. So our free body's pretty well done. Now, there may or may not be a frictional torque here produced by the pin. I'm going to assume that the torque produced by friction is zero or close to it. So basically, I'm saying that I think that the bearing here is pretty good. All right, so we've got our free body, and now I'm going to go ahead and write a Newton's second law equation for it. Except the Newton's second law equation I'm going to write for this is going to be for rotation. So this object is going to start accelerating clockwise. It's going to have a clockwise angular acceleration. So I can describe that by sum of all torques, and again, that's the Greek letter tau, which represents torque quite frequently, is equal to I alpha, where I'm going to call clockwise positive because this thing is going to start accelerating clockwise. And again, in this example, I'm going to sum torques about the pin. You can sum torques about any point you want. The pin is a very good place to sum torques about because both this px and this py go through the pin and hence won't create any torque. All right, so go ahead and write the equation now. The force T1 does apply a force about the pin. The distance we're going to need is this perpendicular distance. Actually probably would be offset a little bit based on the picture. This distance is the radius of the disk. And again, we want the distance that makes a right angle to the force. So the torque produced by T1 is going to be T1 times the radius, and that torque is positive because T1 makes this thing want to accelerate clockwise, and I'm calling clockwise positive. All right, tension 2. The distance we're going to need for tension 2 is like this distance. Again, that's the radius where it makes a right angle. It wouldn't actually be vertical again because this force has kind of a vertical component to it. So the distance we need is kind of like this. That distance does make a right angle. So the torque produced by tension 2 is going to be tension 2 times this radius. And that torque term is negative because I'm summing torques about the pin. I've called clockwise positive, and this tension makes this thing want to rotate counterclockwise, right? Which is the opposite of what I'm calling positive. So this expression represents the net torque about the pin. And by Newton's second law of rotation, that has to equal I alpha. All right, next line, I'm going to go ahead and just put numerical values in everywhere. All right, so tension 1 is going to be 50 newtons. The radius 0.5 meters minus tension 2, 30 newtons. The radius, the same 0.5 meters in this example, equals. Right now, let's think about this moment of inertia. This is a disc-shaped geometry, so its moment of inertia is 1/2 its mass, 10 kilograms, I made that up, times its radius squared. That's going to be times 0.5 meters squared. So there's our moment of inertia of the disk, and then times alpha, the angular acceleration. All right, so there's our Newton's second law problem, or equation applied to this mass. We can solve this for alpha. I'm going to go ahead and do so if you give me a moment. And I think to keep the video short, I'll just pause this and come back when I have it. All right, so I got 8 radian per second out of that. All right, well, now that we know the angular acceleration, now we can go after the delta t here. And in order to do that, what we're going to want is we're going to want to study the motion of our disk here. So I'm going to go ahead and get rid of what I don't need anymore. All right, I don't need this. Anybody watching can always go back and take another look. Clear, okay. And now what we're going to do is we're going to study the motion the same way I always study the motion of just about everything. You've been watching my videos here. I like to graph velocity against time. Tends to be a very useful graph for studying the motion of something. In this case, the graph that I'm going to draw is going to be the angular velocity against time. And although I don't know if I explicitly said it at the beginning, but the intention was that at t equals 0, this thing was starting from rest, meaning that it was not rotating yet. Now, sometime later, the angular velocity I don't know, but it's got to be some numerical value. What I do know is the acceleration, right? We had just calculated the angular acceleration, and I believe I had 8 radian per second. And this quantity here is equal to the rate that your angular velocity changes. Change in angular velocity over change in time, written as an average here. In the language of calculus, this would be d omega dt, right? The derivative of the angular velocity with respect to time. Important to realize, if your angular acceleration is constant, your average and your instantaneous would be equal. So this is the slope of this graph, and what we have found here is that the slope is constant at 8. So it's a linear function because we have constant slope. The slope here is equal to 8. Now that's there's a couple ways I can handle that. So I'm going to let this t be the t for 100 revolutions. I'm going to go ahead and use concepts of slope and area to write a pair of equations here. Equation number 1. The slope, which is 8 radian per second squared, all right, on this picture is rise over run, and that's going to equal what I'm going to call the final angular velocity over this time. Now this equation has 2 unknowns, so I'm just going to move on and write another equation. The other thing I know is this change in theta. Now on this graph, the change in theta is given by this area here. But we got to be consistent with units. If this is in radian per second and this is in seconds, this change in theta is going to come out in radians. So I'm going to go ahead and take this and convert it to radians. We've got 100 revolutions times there's 2 pi radians per revolution. And I better put like radian here so we don't mistake that with a radius. So these are going to go away, and this is going to be what, 200 pi, I guess. Whoops, not 2 pi. 200 pi radians. So the second equation I can write is this. 200 pi radians, and again that would be in radians, is equal to, looking at this graph here, it's going to be this area, which is going to be 1/2 t times the final angular speed. So what we have here is we have two equations, two unknowns, one from the slope, one from the area. So what I'm going to do now is I'm going to solve this, and I'd say easiest way here, I'm going to take this equation and divide it by this equation. So on the left hand side we're going to have 200 over pi divided by 8. And I'm going to go ahead and just get a numerical value here. Okay, so again, 200 pi divided by 8 is 78.5. Looks like, let's see, this would have been in radians, and if I divide it by radian per second squared, it actually works out to 78.5 seconds squared equals. All right, right hand side. Now when we take this and we're dividing by this, an important thing to realize is these are going to cancel right here. Boom, boom. And if I take t over 2 and we're dividing that by 1 over t, that's effectively going to be t over 2 times t over 1. So that's going to give me a t squared over 2 on the right. So again, go ahead and write it out. I'm not going to, but if you're observing, if you take this, divide it by this, here's what we end up with. And this equation we can solve for t quite easily. Let's see, multiply by 2 and square root it. And get 12.5 seconds out of that. So, okay, looks like it's going to take 12.5 seconds for this to come up to 200, to rotate around 200 pi radians. If I wanted to, I can find the angular velocity easy enough. I can talk about how I would do that here. Let's see, I can get it right from this. The actually looking right here, the 8 radian per second squared is equal to our final angular velocity over our time, and I know our time here, so we could find that angular velocity easy enough. But anyway, the purpose of this video was to demonstrate, how to apply Newton's second law for rotation, and then couple it with a motion study, or how to study the rotation of the motion of a rotating object. And hopefully this has accomplished that. Have a great day.